Hello you guys, today I'm going to be teaching you how to derive an analytical expression for velocity using the continuity equation and equation of motion. Let's go ahead and get started. The first step in finding the velocity is choosing an appropriate control volume, and I did so labeled here in red, and it's the gap thickness between the ram and the cylinder wall, delta. That's important because it's the only area with liquid moving, and that's because of the velocity here, u, moving the ram, and that's pushing the liquid towards the left. So that's why that is our control volume. The next step is finding your assumptions. Here we have that it's a constant velocity u going towards the right direction, and that constant velocity basically tells us that it's a steady state process. Another one of our assumptions is that it's a incompressible liquid, so the density doesn't change. Another assumption is that the gap thickness between the ram and the cylinder, delta here, is really small. So the radius is way bigger than this little gapped area here. And that's the area that we're interested in. And another one that isn't too intuitive is that the velocity in the z direction and the y direction go towards zero, but when you look at the system it makes sense, because if there's velocity of the fluid acting in the y direction up, it would also act down here, and so that would cancel each other out. It's the same with z. If it would act in towards the page, it would come out of the page, so that would cancel out. The next step is simplifying the continuity equation given here in Cartesian coordinates, and we know that the density of the liquid doesn't change, so any change in rho is basically zero. So that cancels out, and so do all of these because of that. And we know that there's no velocity in the y or z direction, so these two would cancel out. And what we're left with is that rho del vx and over del x is equal to 0. And that tells us that the velocity in the x direction is only dependent on the y. That's important for our next step. The next step is simplifying the equation of motion, and it's very similar to the last step where we use our assumptions to cancel out terms. We know that there's no velocity in the y or z direction, so any term containing that would cancel out, which would be all of this and all of that. Also all of these. There's no pressure buildup in the y or z directions, and if there was, because of symmetry, those would cancel out. Our system doesn't produce any gravitational terms itself, so these cancel out, and that one would cancel out as well. We know that it's a steady state process, so that cancels out. By the continuity equation, this cancels out, and again, there's no Vy or Vz. There is a pressure gradient in the x direction, and that's what causes the liquid to move. Then we know by the continuity equation that cancels out, and we know that it's only dependent on y and not on z from the previous steps. So what we're left with from the equation of motion is this right here. The next step is determining the proper boundary conditions. And here we know that at radius r, which is not drawn to scale at all, as we know, is equal to negative mu, and that's just because that's how our system is set up. This is the positive x direction, so the velocity at r is negative u because it's pushing it towards the negative x, so that's why it's negative u. And we know that up here, by the no-slip boundary condition, the velocity there is equal to 0, so that's how we get this bottom term. So the next step is deriving an analytical expression for the velocity of the system. So using the simplified equation of motion and using the pressure gradient, assuming it's constant for now because it's a steady state, so it's just a constant alpha. We then integrate both sides using some algebra, and we do this and we find this equation here. And so to find C1 and C2, we use our boundary conditions, and so we solve out for C2 and C1, which I know you guys can do. And that's how you find the velocity profile for the system. Make sure to hit the subscribe button